All right, practice makes perfect. Let's take a look at problem 3. So we're told a pressure enthalpy P versus H diagram is a common tool used to analyze power generation in refrigeration cycles. It is therefore desirable to plot isotherms, constant H, and isentropes, constant S. Derive an expression for the slope of an isentrope, dpdh at constant S, and the slope of an isotherm, dpdh at constant T. Since we ultimately would like to plot isotherms and isentropes using an equation of state, the only variables that may appear in your final expression are PVT, CP, and CV. Alright, sounds like fun. Well, looking at A and B, what stands out to me is here we're interested in differentials. Okay, and so we're not looking at an expression for, say, differential with independent variables T and P, but here we have the differential of P with respect to H at constant S. So I'm already looking at first derivative. Okay, and so if you kind of go back to our procedure for getting expressions for differential of, say, H with independent variables T and P, all right, we're already kind of at that second step where we're looking at simplifying. So if I'm looking at A, okay, and I want to get dP dH at constant S, all right, do I have a heat capacity relationship or a Maxwell relationship? I certainly know I don't have a heat capacity relationship. Do I have a Maxwell relationship? No, because my Maxwell relations relate S to P, V, and T. Okay, so what am I going to do? Well, I go back to my fundamental equation for H. I can't remember my fundamental equation for H, but I remember my combined statement of the first and second law, which gives me my differential for U, that du is equal to TdS minus PdV. Then to get my differential for H is my convenience function defined as U plus PV, where the goal of H is to switch the role of the conjugate variables P and V. Okay, so dH is equal to T ds plus V dP. Right, the sign of that term changes. All right, so I need dP dH at constant S. Okay, so normally I would think about dH dP at constant S, but working with P in this case is going to be just as fine. So I'm going to go through and I'm going to divide by H. Okay, and the reason it works fine here is here I'm looking at H, say with independent variables P and S, and what do you know? The natural independent variables of H are P and S. Okay, so I divide through by dH. Since I can only differentiate with respect to one variable at a time, I'll hold the other constant. And so in this case then, I'm going to hold S constant. Okay, so these should become curly. These are curly differentials. In doing that, let's see what we're left with. dH at constant S, so this is dH, that's 1. I have T, or ds at constant S, so now S is being held constant, so the derivative of a constant is 0. Okay, plus V dP dH at constant S. Okay, so V dP dH at constant S, right? dP dH at constant S is what we're trying to solve for. Okay, so we find that this gives us dP dH at constant S is equal to 1 over V. Okay, so dP dH at constant S is just equal to the inverse of the molar volume. Cool. Okay, easy enough. Slope of our isentrope is just 1 over V. Cool. Got it? Now let's look at B. Okay, so now B, we want dP dH at constant T. So we'll try the same thing. So I don't have a Maxwell relationship or heat capacity relationship to plug in here. So I go back to my fundamental equation. Here we're thinking about fundamental equations for H, right? Because when we think about fundamental equations, they're going to be U, H, A, and G. We don't have one for S because S is just found from taking our equation for U or H and solving for S. Okay, but I'm going to go back to our relevant fundamental equation and try and work out an alternative expression. Okay, so starting with what we had here, okay, fundamental equation for H is dH is TdS plus V dP. Okay, and what I'm going to do is I'm going to start by doing exactly what we did last time. Okay, we'll find it doesn't work. Okay, spoiler alert. But, when you're solving these problems, you're just going to have to take a leap of faith and give it a try. Okay? Then if it doesn't work, rewind and come up with an alternative strategy. So here then, if I want dp dh at constant t, okay, I want dp dh at constant t, I'm going to go through, I'm going to divide by dh. Okay. Then I could only differentiate with respect to one variable at a time. So I'm going to need to keep a second intensive variable fixed. In this case, I'm going to use t. Okay. So what does this leave me with? This would leave me with dh dt, or dh dh at constant t. Well, dh dh is just going to be 1. Okay. Is equal to t ds dh at constant t. Well, that's just t ds dh at constant t. I can't really do anything with that. Plus v dp dh at constant t. All right, where dp dh at constant t is, the quantity I'm interested in, I'm after. Okay, but when I do this, I'm stuck, right? I'm stuck because I have a ds dh at constant t. Now I could look at our equation sheet to see if we have a Maxwell relationship or heat capacity relationship, but we don't, right? And I know I don't have a Maxwell relationship because our Maxwell relations relate S, P, V, and T. Okay, so that's not going to work. Now, before when we were stuck, we said, well, let's go back to our fundamental equation and work out an alternative expression. But here, that's not going to do anything for us because our fundamental equation for S is just taking our fundamental equation for H and resolving for S. So that's not going to help us out at all here. Okay, so what do we do? Where do we go wrong? Okay, and so what I'm going to do is I'm going to go back, okay, to our fundamental equation for H. Okay, so I'm going to say dH again is TDS plus VDP. And all I'm going to do is I'm going to take a slightly different approach. Okay, what we want is dP dH at constant t. Now, if you think back to when we had worked back, okay, so let's do flashback. Okay, if I do a flashback, okay, so remember when we worked out our expression for the differential of H with independent variables t and p, we had dH dt at constant p dt, this was just Cp, okay, plus partial H partial p at constant t dp. And I know for this term here, we had went back to our fundamental equation for H, worked out an alternative expression, found a Maxwell relationship that we could plug in and nicely simplify that term. Why can't I do the same here, right? Looking, what I want is dP dH at constant t. I've done this before for dH dP at constant t, right? So why not do exactly the same thing? Because if I can calculate dH dP at constant t, then dP dH at constant t is just the inverse, right? The related via inverse relationship. So I know that dP dH at constant t is just equal to 1 over dH dP at constant t. So if I can find dH dP at constant t, I've got my answer. And since I know that I've done it before, let's do it. Okay? And so basically, here we had tried to divide by dH, so differentiate with respect to h holding t constant. And where we got stuck is this term. We don't have a Maxwell relationship we can work with. So we're just going to go back and we're going to take this on in a slightly different way. Okay, where here, instead of thinking about dP dH at constant t, I'm going to think about dH dP at constant t. Okay, the inverse. So I'm going to divide through by dP, divide my differentials by dP. Okay, can only differentiate with respect to one variable at a time. So here I'm going to hold t constant. Bam, bam. Okay, so now I have dH dP at constant t is equal to t ds dP at constant t plus v dP dP at constant t. So this is dP dP, so that's just going to be 1 plus v. All right, now looking at this term, now instead of ds dH at constant t, I have a ds dP at constant t. Here I know I have a Maxwell relationship, right? I know my Maxwell relations are going to relate S to P, V, and T. Okay, so going to our equation sheet, we're going to end up with Okay, I'm going to write a t here. Okay, ds dp, oh, and actually calculus of thermodynamics, here's my inverse relationship looking at me. But going down to my Maxwell relationships, what do we have? ds dp at constant t is this one here. ds dp at constant t is negative dv dt at constant p. So this then will be negative t dv dt at constant p plus v. Great. Okay. Then finally, if I want dp dh at constant t, that's the same as 1 over dh dh dp at constant t, which will be equal to 1 over v minus t dv dt at constant p. Okay. Cool. Okay. So, tried approach 1, it didn't work. So I rewound, acknowledged that I might be able to leverage a reciprocal rule and tried to solve for the reciprocal instead. And we found that that worked. All right? And we end up getting this final expression that dp dh at constant t is 1 over v minus t dv dt at constant p. All right? Cool. Hope that helps.